Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. Today's paper I want to talk about high-performance aerospace components designed with architected cellular materials. This paper comes to us from researchers at the University of Illinois Chicago and Santa Clara University. Now, if you're like me and you weren't super familiar with these aerospace composites, let's begin with this diagram. Here we see an example of conventional honeycomb-based alongside IRCM core composite sandwiches. No surprise that in the aerospace industry, you want to be as light as possible without sacrificing the properties that you care about, be they mechanical, thermal, or otherwise. And in the past, they've relied on these honeycomb and similar type of structures, which have their strengths, but they also have some weaknesses compared to these alternative IRCM structures, which stand for implicitly represented core materials or architected materials. Right? For example, the honeycomb structure does not have connected voids, but the IRCM does. The parameterized IRCM can have shear rigidity, whereas the honeycomb does not. And architected conductivity, same thing you can have in IRCM. In the introduction, the authors talk about the importance for these things in next generation aviation components and really the multiple different properties that you have competing with one another. Mechanical properties, corrosion resistance, environmental conditions, thermal properties all have to be present. So from a design perspective, this is challenging. But we have some cool new things happening. For example, additive manufacturing allows us to make shapes that we were never able to make before. We can end up with really, for example here, complex porous nature of these novel cellular structures, which are great, but we have to figure out how to design them. The second challenge is figuring out how these complex structures lead to modeling challenges and figuring out how exactly do you slice and toolpath plan these things for additive manufacturing. So this team is using implicitly represented cellular materials, IRCM. The key here is that these have open and continuous voids. So for example, if you wanted to flow a fluid through this material for, say, thermal management, you could do that. They do that for load bearing, de-icing, and blast resistance. One of the benefits here is that IRCMs are parameterizable and computationally light. So when you go to predict their properties, mechanical or otherwise, you can do so with homogenization methods. Here's an example, right? Here's several different materials, and they're showing how with different equations, right, different functions, implicit functions, you can achieve this nice tunable density, right? You can go from low densities up to much higher densities. In fact, they show with 5 different implicit functions how you can go from the unit cell to the SBAM core and show how it actually would scale. Because these things are lightweight, because they're parameterized, doing mechanical and thermal simulations are fairly straightforward and not very computationally intense. Here they're able to show you how 2 different designs, they're able to do multi-objective optimization, simulating both the mechanical response and the thermal behavior to figure out what would be the best parameters to use to get the objectives that they have of interest. Ultimately showed some significant improvement, basically between 13 and 26% improvement. Here in this case, it says compared to the design and the uniform density for all cells, the average temperature for the first optimized structure was reduced by 13%. That's going to be relative to the standard honeycomb structure. It says the second optimized structure was reduced by 11%. Down here, they show another one that compared to the uniform density for all unit cells, the average temperature was reduced by 26% as a result of this topology optimization. There's lots of other benefits to doing this. One of them is that you don't have to generate an STL file. People that have done 3D printing know that you come up with some sort of model or shape. You have to turn that into the standard triangle language, right? This mesh of triangles to figure out how you're actually going to print it. But they don't have to do that here by using these implicitly represented functions. So I hope you'll check it out. This is a really cool paper, and you can learn all about it in the latest issue of IMMI.